So section P2, we're going to take a look at exponents. We briefly touched on exponents last time, didn't do very much, but we did briefly touch on exponents. But we're going to go a lot further this time, and we're going to start out by talking about some properties of exponents that you're familiar with. Maybe you haven't seen them used in a while, that's fine, but you've seen them before. So the first one talks about what happens when we have a to the m times a to the n. So does anybody remember how we can consolidate that and write it more simply? Very close. It's a to the m plus n. So when we have exponents that are doubled like that or written that way, we actually end up adding the exponents together. When our exponents are written as a division, right, a to the m divided by a to the m, if multiplication becomes addition of exponents, then division should become subtraction of exponents. The third one actually feels a lot like the first one, but it's different. I don't have the base repeated. You'll notice there's parentheses that show up. What ends up happening is that I have a power raised to a power, and that's the one that you end up multiplying then with. So we have a to the m times n. The other two power rules feel quite similar, and they feel kind of like what happens when we do distribution, which we talked about last time, of like multiplication over addition or multiplication over subtraction. So we're going to actually distribute the exponent over the multiplication or the exponent over the division. So this is a to the m times b to the m, or a to the m divided by b to the m. Okay, does that look familiar? I hope it does. This whole chapter, chapter P, is supposed to be things that you've seen before. So if there's a significant portion of things in this chapter P that you're like, I haven't seen this before, we need to chat, okay, because there's a problem. There's a disconnect somewhere, and maybe this isn't the right class for you. But if you're like feeling like I already know how to do this, that's where you should be, because this is a review chapter. Negative exponents. For negative exponents, we actually use the reciprocal. So the reciprocal of a is 1 over a. So the reciprocal of a to the negative n, or the value a to the negative n, is the same as its reciprocal 1 over a, and then that's to the n. So there's a note here in the middle. There's a note, it's also on your notes, that talks about in general what you need to make sure you're doing on all problems when you get to the end of them, is that you shouldn't have negative exponents. So if your exponents are negative, you need to change their location. If they're in the numerator and the negative, you move to the denominator, or vice versa. The last one that we're going to talk about is a to the 0. What's a to the 0? Yeah, it's 1. So a to the 0 is 1. I'd actually like to show you why this one's the case, just real quick, because it's very nice and clean, and it's kind of a clever approach. The number 0 can be written, and I'm just going to use the number 3. There's nothing special about 3 except it's not the letter n, okay? 3 minus 3 is 0, right? Sure. The property over here that's at the very bottom, I didn't say that right, number 2. It's number 2. We can actually use that problem from the right-hand side back to the left-hand side. So instead of having it written as 3 minus 3, I can actually rewrite this as a cubed over a cubed. And what happens when you divide something by itself? It's 1. So that's actually an actual proof of why this is true, except that if I were proving this, I wouldn't use 3's, I'd use n's. But that's why this works. So I'm not asking you to argue why anything works in a general statement, but we are going to use these properties to rewrite with exponents our values. So if we have the ability to rewrite it without exponents, right, like the first one, it's 5 cubed, we will. If we can't, on number 3, a to the 7th, we just leave it as a to the 7th kind of stuff, okay? So on the first one, the first thing that you should notice, because we talked about this last time, is that negative 3 power is not on the negative 5, it's on the 5. Do you remember talking about that? It matters. On this one, it actually doesn't end up mattering because of the particular values that we're using, but sometimes it will. So keep in mind this negative in front is sort of isolated from what else is going on. So I'm just going to write it first, and then we're going to deal with the 5 to the negative 3. So the last property over here, number 4, that we talked about is the property we'll use. So I end up with 1 over 5 cubed. So that's the property of exponent in play. And then we'll do the same thing that we did last time. We will actually evaluate or simplify 5 cubed. So do you remember what 5 cubed is? Yeah, it's 125. So this is negative 1 over 125. You got to show me something. I fully recognize that many of you have calculators where you could put in the original thing given and it will spit back out to you some fraction form of this value over here, or it might even turn it into a decimal and you turn it back into a fraction. There's got to be some intermediate steps throughout so that we can see those properties at play. Number 2, we have a couple of different pieces. Notice that they are added together. So we can't combine the first piece and the second piece the way that they're currently written because it's addition. And none of these properties over here talked about what happens when there's addition. The only one that we had that talked about powers is with multiplication. It's down here at the bottom on the power rules. So we're going to deal with each of them sort of separately and then see if we can combine them at the end. So the 6 to the negative 1, how can that one be rewritten? 1 over 6. There's addition. And then what's 5 to the 0? It's 1. So there's a couple of things that you can do. If you want, 1/6 plus 1 is 1 1/6, then that's perfectly fine. Or there are going to be cases where we might want to move forward with a problem and turn it into an improper fraction. If we did, what you'll remember is that you multiply and then you add. So 6 times 1 is 6, plus 1 is 7. So if this is written as an improper fraction, it's 7 over 6. You might see the back of your book change something into an improper fraction. So I kind of want you to know that you can, but I don't need you to either. It's okay if you leave it as 1 1/6.
But either one of those are right.
Yeah, either one of those are perfectly fine. You bet. All right, number 3 has a lot of multiplication to it. I've got multiplication inside the first set of parentheses, but there's no cleaning things up inside the first set of parentheses. I've got multiplication in the second set, but there's no cleaning things up in the second set either. So really, those parentheses there are sort of irrelevant. We use parentheses sometimes to indicate multiplication, but sometimes things just beside each other indicate multiplication as well. For instance, right here, the fact that the negative 6 is right beside the 8 to the 7th means they're multiplied. Right? I mean, that they don't really need parentheses to mean that. They just mean that because of the way that they're written. So all of this is being multiplied, which means I want to group the things that actually can be combined together. Whether you write them out or whether you just think them out, that's fine. The negative 6 and the 3 can be multiplied because they're alike, right? They're just they're just integers. So what is negative 6 times 3? Negative 18. The next thing we'll look at is we'll look at the a's. So I have a to the 7th and I have a cubed. That's property number 1. I have a to the 7th and I have it multiplied by a cubed. So what will I do? Add the exponents. So that gives me a to the 10th. And the b does the same thing. I have b to the 4th and b to the 5th, which will give me b to the 9th. And because all my exponents are positive, I'm done. Any questions so far? Okay, I have a few more. Obviously, they're getting more complicated as we go. That's the whole point. More going on in the problems. On number 4, one of the things that you might notice to begin with is that there's a negative in the numerator in front and a negative in the denominator in front. Okay? And what happens when you divide a negative by a negative? It becomes positive. So there's no need to continue writing those negatives as we work. They're already eliminating one another because a negative divided by a negative is positive. So now I've already cleaned it up a bit. I've removed 2 negatives. There are several things that you could do to solve this problem. Let me show you a couple of them so that you can kind of think, oh, that one made more sense to me, and you can do it from that way, that way from now on. So one of the ways that I think makes the most sense to me is to simply eliminate negatives. So on the top, I've got that p to the negative 1. Well, one of the things that's true is that it becomes its reciprocal. Well, what that means, because there's already a fraction, is that I can simply move it to the denominator and write it p to the positive 1. So I tend to move things. I would move this one down, and I would move this one down, and I'd move this one up. And now that's messy, so I'm going to erase it. But I'm going to shift everything. This is one option. I'm going to shift everything that has a negative exponent. So let me do that as my first option and show you what that would look like. Now, first of all, not first of all, but the 3 is not going to move. The 3 does not have an exponent. Okay, so the 3 is going to stay put. The p as well, that's already in the denominator, has a positive exponent. We don't see it, but it's the number 1, so it's not going to move. So those pieces are staying put. And I'm going to shift things one at a time. So I'm going to first shift the p to the negative 1, which means I'm going to have p to the 1 in the denominator. And then I'm going to shift the q to the negative 1, which means I have q to the 1 in the denominator. And then the last thing is that I'm going to shift the q to the negative 3, which means I have q cubed in the numerator. Okay, so this is one way of trying to simplify what's there because I've eliminated all my negative exponents. Again, the 3 is not going to move, but we can consolidate some things. I have p to the 1, and I have p to the 1, so we really just have p squared on bottom. And on top, there are 3 q's, right? I could write that this q, 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 and on bottom there's 1 q. So I can eliminate one of those q's so that I still just have 2 on top. So whether it's because I was taught that way or whether it's because my mind simply works that way, this is the way that I tend to work with problems. Another option, and certainly still not the only other option, but another option that I'd like to show you is more just following the exact rules that I gave you. So for example, again, like I told you that the 3 is not going to move, but let me move this up so it's a little bit out of our way as an option, but it's still there. So the 3 is not going to move, but what I'm going to do is I'm going to subtract exponents, which means the p that's in the numerator that's got the negative 1 is going to stay there. But there's a p in the denominator that also has a power of 1, and I'm going to subtract that. So it's p1, negative 1 to the negative 1 minus 1, because I subtract anything that's on bottom. Okay? Same thing with the q. The q has a negative 3. I'm sorry, it's not, negative 1. And then this negative 3 gets subtracted, so it's minus negative 3. I'll write it that way to start with, minus negative 3. Okay, so I'm just absolutely using the property over here, number 2. If it's in the numerator with an m, the denominator with an n, I subtract n minus m, whether they're positives or whether they're negatives, and I'll deal with where things actually end up being positive or negative at the end in a minute. So that gives me p to the negative 2. And then the opposite of a negative, right? So the negative 1 minus negative 3 is negative 1 plus 3. So that's q squared over 3. So that's consolidating, combining those exponents together. And then anything that's a negative exponent is going to shift. In this case, the p to the negative 2 will go down and be p to the positive 2 in the denominator. Okay, so there's nothing about either of these methods that you can't do. They're both correct. They're just a slightly different approach in thinking about it. Okay? Sound good? All right. So on number 5, actually, so what I'm going to do as I go through some of these others is that we might recognize, hey, we could have done this. I'm just not going to show it to you multiple ways. I did one of them in a couple of ways so you can think about it. So if my way that I'm suggesting but not doing is the one you'd like to do, then go for it. And we'll make sure we get the same thing when we're done. Okay? On this one, I have a negative 4 exponent. So a couple of different options that we could do. We could take this exponent and we could distribute it in. Like that's one option. Okay? The other thing that we could do is because it's negative, we could flip it first and make it a positive 4, and then we could worry about the distributing it in. So it doesn't matter to me. So do you want to distribute the negative 4 or do you want to flip it and distribute a positive 4? Y'all tell me. Which one? Flip it? Okay, we'll flip this one, okay? So the fact that it is negative means that I can flip it upside down. So it means that everything that was on bottom, which was x to the negative 4a plus 1, is now on top. And what was on top, x to the 2a minus 3, is on bottom. It's still raised to an exponent, it's just that the exponent's positive now. Okay? And then we're going to distribute the 4 in. So what does that look like? Well, it means that this is going to be multiplied by 4, and this is going to be multiplied by 4. And the property that I'm using to do that is the first power rule property. When I raise a power to a power, I multiply the powers. Okay? And I'm also using the third power rule because I'm doing it to the top and I'm doing it to the bottom, of course. So I'm going to multiply. So if I multiply 4 times negative 4a, that's negative 16a. And then I multiply the 4 times 1, that's plus 4. And then on bottom, I have the 2a minus 3. So I'm going to distribute the 4 to that. So 2 times 4 is 8a. And the negative 3 times 4 is negative 12. It's kind of tempting to stop here, but I actually cannot. Does anybody see why? It's not because of the negatives, although we'll talk about that in a second.
Divided all by 2.
It's not because it's divided by 2. You're thinking about the fact that there's a lot of even numbers, I think. It's not because of that. What was that?
Like simplify it more.
But it's not what, that's not what it is. There's something as simplified, but it's not what you just said.
Take off x's.
We can't cancel the x's, but you're getting closer.
Can we cancel my a's?
Nope.
Is it the addition and subtraction?
That's what it is. You got it. So notice over here, property number 2. If I have a base to a power on top and the same base to that power on bottom, I can consolidate to a single base by subtracting the powers. Right? That's actually what I have. I have the base x raised to a power divided by that same base x raised to the power. Yeah? So as I think about this next, and I could have done that from the beginning. I didn't mention that because, to be honest, that's not where my mind went initially. But it would have been an option. We could have consolidated them in that way right here because they have that same property there. So I need to take the first, or the top exponent, negative 16a plus 4. And I need to subtract the bottom exponent, which is 8a minus 12. Okay, is everybody okay so far? I'm going to rewrite it. You don't have to if you can do this without having to rewrite it. It's okay. But I'm going to go ahead and distribute the negative through. So this is negative 16a, positive 4, negative 8a, and positive 12. And then we can combine the a's and the constants. So I have negative 16a and negative 8a, which is giving me what? Negative 24a. And then I have positive 4 and positive 12, which gives me positive 16. So this is actually my answer. And let me talk about why we don't have to sort of put it back in the denominator because we do see a negative. Because it is tempting to want to do that. It wouldn't be wrong if you did it, by the way. The reason we can leave it right here is because I don't know what a is. If a is 0, then my exponent is actually already positive. Because negative 24 times 0 plus 16 is a positive number. Right? But like if a were 1, negative 24 times 1 is negative 24 plus 16. That would be a negative. So sometimes this exponent is negative and sometimes this exponent is positive, which means it's fine to have it written this way because there's not an option that actually for sure ensures that my exponent is going to be positive in the numerator or positive in the denominator. Cool? All right. So this is an interesting one. There was a lot going on in that problem. There were several different ways we could have started it. All right, there's one more in this set of examples, I believe. We had used the idea last time of flipping it instead of distributing first. I'm actually going to approach this one a little bit differently just so you can see another option. It doesn't matter to me which options you pick, but just so you have a choice. The first thing I'm going to do on this one is I'm going to actually consolidate the insides because I actually can, much like I talked about at the very end on this one. We could have consolidated the inside first. So I'm going to do that on this one just so we can see how that would look. 15 and 18 actually reduce. What do they both have in common? Yeah, the 3. So the 15 divides by 3 for 5. The 18 divides by 3 for 6. I'm going to move my x to the negative 2 down on bottom. Because like I told you, that's how I usually think about them, is shifting things that way. So right now I have a negative. I have a 5 on top. I have a y to the 9th on top. I have a 6 on bottom. I already had an x squared on bottom, and now I'm going to have another x squared on bottom. And I have a y to the 8th on bottom. Is that all right for everybody? So I consolidated, or I reduced the 15 and the 18 to give me 5 and 6. And I moved the x to the negative 2 that was here to the bottom to make it x to the positive 2. Those are the two steps I did. I'm going to combine the values that have like bases now. For example, the x to the negative 2 that's on bottom is now x to the 4th. The y to the 9th on top with a y to the 8th on bottom. 9 minus 8 is 1. So I actually just have y to the 1 or y on top. I think I will just write to the 1 right now just to remind us that it's there. And then I'm going to do what we did last time where the negative flips it. So I'm going to do that next. When I flip the negative in front, there's nothing that changes, so that stays the same. But I have 6x to the 4th on top, and I have 5y to the 1st on bottom, and now it's to the power 2. Is everybody okay to this point? This one's a little bit different than the last one with that power on the outside. The thing that makes it different that I'd like to point out is that there's coefficients in these, right? There's a 5 and a 6. And that power on the outside applies to the 5 and the 6 as well. So on this one, as I distribute that exponent through, it has to distribute to the x, the y, and the 5 and the 6. Not only that, but it also has to distribute to the negative, right? So squaring means I actually have something multiplied by itself. So what is a negative times a negative? It's positive. So the squaring of that negative in front is going to give me a positive. I'm going to go ahead and write it just to remind ourselves that that actually happened. We didn't just lose the negative. You don't need it written in your final answer. So the first piece is 6 squared. So 6 squared is 36. Now I have x to the 4th squared. X to the 8th, right? I multiply the exponents. I have 5 squared, 25. And I have y to the 1st, or y squared. So it's y squared. Okay? So whether you group that positive that I did in the front with it or not, it is a positive number. This is the result that we get. I can't combine the x to the 8th and the y squared on bottom, of course, because the bases are different. Right? I don't have any properties that says you can combine them when their bases are different, only when the bases are the same. All right, any questions on those? Because we're about to shift gears a little. Yes, ma'am.
Can you just explain how that ended up being positive? Because we flipped it? Or like
It's not positive because we flipped it. It's positive because it was squared. So when I square things, it means I multiply them by themselves. So I end up multiplying a negative times a negative. That's what squaring does. So I end up getting a positive that way. But it is something that people often forget that it distributes to the exponents, to the constants, and to the signs. So you have to remember that it distributes to every single piece. All right, so shifting gears a little, and there's a reason that this shows up in here, but we're going to talk about scientific notation. The reason it shows up in this particular section is because scientific notation involves exponents, and we just talked at length about exponent properties. So scientific notation looks like a times 10 to the n. The a value is between 1 and 10. So it is a single digit number. It might have decimals. That's okay. But it's between 1 and 10. And then the n value, that exponent, has to be an integer. So it can be positive. It can be negative. Technically, it could be 0. It's just highly uninteresting when it's 0. But that's not excluded. Okay? So positive, negative, 0, integers. And what we're trying to do is we're trying to be able to move in and out of scientific notation. Scientific notation is really valuable when you're trying to do one of two things. Represent something that's extraordinarily large, right? Like the distance from here to the sun. We don't want the there's too many zeros involved, right? You need something a little bit more consolidated, so scientific notation, or representing something that's extraordinarily small. So if you've dealt with things in chemistry, right, molecules and atoms and stuff like that, very, very, very small things. So this is not like something we use in our everyday going about things business, but lots of people do because of their line of work. So that's where scientific notation comes into play. But it's actually pretty easy to use. So scientific notation actually involves simply moving decimal places. So right now, this one's going from scientific notation into standard notation. And I tend to explain this in a slightly different way than a lot of times people do. So a lot of times people will talk about if the exponent's positive, you do this. You move it left or you move it right. If the exponent's negative, you do this. You move it left or you move it right. And they always reference left and right. I don't reference left and right. I reference, is it bigger or is it smaller? Because then you know whether to move it left or to move it right. And the nice thing about that is because it works whether you're going from standard to scientific or scientific to standard, and I don't have to switch, oh, now I'm going the other direction, so now I have to change the word left to the word right, which starts to be a little confusing. So in particular, what you see here on the first one is you see a power that is positive, right? A positive power means that it's a large number. That's really what it means. And on the second one here, you see a negative value. And a negative value means that it's a small number. So if you can keep these ideas in mind and then move decimals to create numbers that do that, then you're golden. So right now, those numbers are both 5.98. If I need to make 5.98 by moving the decimal point bigger, where's the decimal going? It's going to the right. And the 5 tells me exactly how many places it's moving to the right. It's going to move to the right 5 places. So I have the decimal right here now, and I'm going to put a bunch of zeros here on the end, and then we'll shift. So I'm supposed to move it 5 places. Here's 1, 2, and then 3, 4, 5. That's where it will stop. So my number will be 598, and it will have 3 zeros after it. So it's 598,000. On the second one, I have a negative exponent. Negative means that my value is a small value. If I have the number 5.98 and I want to make it smaller by moving the decimal, which way does the decimal go? To the left. So I have my 5.98, and I put zeros in front of it, and I move it left, in this case 2, because the exponent's a 2. So here's where my decimal point will stop. You can either write this as the decimal point, the 0 and the 598, or you can write it with the 0 in front. It is absolutely the exact same thing, whichever one you like. My daughter was working inside of an online math system the other day, and she asked me, will it matter if there's a 0 in the front? And my answer was, it shouldn't. Have it there or don't have it there. It's the same number. It shouldn't, but we're about to find out. And it was fine. But yeah, it doesn't make any difference. Either of those are versions of the same answer. So positive exponent makes it large, or it is a large number. A negative exponent, it is a small number. And we can do the same thing when we work from standard into scientific. So we're always trying to create a number that's between 1 and 10. So looking at this number, 16,587,000, where would you have to put a decimal place to create a number between 1 and 10? Yep, right behind the 1 or between the 1 and the 6, right? So the number that I'm going to start with is a 1 with a decimal point, and it's 6,587. So we're not going to shorten any of the numbers that we have, except for the zeros at the end. Okay, I don't need to write the zeros at the end, but I'll write everything else that I have. And this is times 10 to some power, and we figure out what that power is by how many places we move the decimal. Now, you might look at number 9 and say there's not a decimal, and you're right. So the understood location of the decimal is at the very end. Okay? So if I move this decimal, this is 3 places. This is 6 places. That would be 7 places. So the exponent's a 7. And then I asked myself, was the number big or was it small? It's big. So is it positive or is it negative? Positive, because big values, large values are positive exponents. They go hand in hand. And we could do the same thing on number 10. Looking at all those digits that are there, where would I have to put the decimal point to create a number between 1 and 10? Between a 9 and the 8, or after the 9, yes. So I would do, 9.81. That's my value that's between 1 and 10 with the numbers I'm given. It's times 10 to a power. And I'm going to count. So this is 2, 4, 6, happens to be 7 again. But was my value that I was given, rather, small or large? It's very, very small. So my exponent should be negative. Small number, negative exponent. Okay, so in some sort of sense, you're like, well, yeah, there's exponents there, but that doesn't really utilize anything that I just showed you and proved and talked about exponents, right? So I want to give you an example of one where we're combining this idea of the scientific notation with what we're allowed to do with scientific notation, including the exponents. So the last example in this section is example 11, and it talks about what happens when we try to divide scientific notation values. You're going to have some in your homework that will be multiplying the scientific notation values as well. So we're working piece by piece. This is actually much like this problem over here that we did on number 3, where we considered the coefficients individually, and then we considered the bases with the exponents individually, right? And looked for ways to combine them. We're going to do the same thing here. So I'm going to consider this piece first. 9.3 and 3.1 actually divide nicely. What is 9.3 divided by 3.1? Close. Close. It's just 3. That's just 3. And you're welcome to grab a calculator to confirm things, of course. It's just 3. 9.3 divided by 3.1 is 3. But now you see bases. They happen to not be x's or a's or b's or y's or whatever we were doing before. They're 10s. But they have the same properties as the exponents when they had the variables, right? I have 10 to the 12th on top. I have 10 to the negative 5th on bottom. So you can either think I'm going to move the 10 to the negative 5th that's on bottom because it's on bottom up and make it positive 10 to the 5th, right? 10 to the positive 5. Or you can think about it as subtracting the exponents. So I'll write it as subtracting the exponents since I haven't done that very much. 12 is my top exponent, minus the negative 5 in the bottom. And of course, subtracting a negative is the same as addition. So 12 minus negative 5, or 12 plus 5 is 17. There's one word of caution when you get to the end of a problem working with scientific notation. You've got to make sure that the answer is in scientific notation. So usually what happens if it's not is that you ended up with something in the front that's not actually a number between 0 or between 1 and 10. 3 is. So we're good here. Let's just pause for a moment and consider what would have happened if we had actually had an answer here, like this answer had given me something like 30 times 10 to the 12th, right? It was 30 instead of 3. But I'm not done because the answer's not in scientific notation yet. I would have to put a decimal point here to make it so. Then it would be a 3, right? But you can't just take a 0 away and not change something else to compensate. It doesn't work like that. So as we're taking a look then at the exponent, as we have changed that number and made it smaller, it was a big number, right? So I have to compensate to make the exponent bigger as well. Because I made the number in front, it was big, now I made it small. So I have to do the opposite to the exponent. So now it would be 10 to the, in this case, 13. Okay, so I think there's one that shows up in your homework where you have to do that at the very end as you're considering it. I think it's a multiplication problem. Any questions on exponents or scientific notation? All right.